India. So today we are very privileged to have amongst us Professor Prajwal Shastriji, who will be speaking on meandering into astrophysics. Our respected Madam, respected Chancellor Professor Amit Banerjee ji, and also Subhankar ji from the Academic Trust. Ladies and gentlemen, let me have the privilege of introducing today's speaker to all of you. Prajwal Sastry is an astrophysicist of over 4 decades. She investigates the physics of giant black holes that are found in the centers of distant galaxies using telescopes at multiple frequencies based on Earth as well as in space. She got her PhD from the Tata Institute of Fundamental Research, and after postdoctoral research positions in the University of Texas at Austin, University of California at Berkeley, and the Harvard Smithsonian Center for Astrophysics, she was a faculty of the Indian Institute of Astrophysics, Bengaluru, for 23 years. She has been a Fulbright Fellow at Stanford University, Senior Associate at TIFR ICTS, and Senior Fellow at the International Center for Radio Astronomy Research, in short ICRAR, Australia. She is currently Emeritus Scientist at the Raman Research Institute and Adjunct Professor ICRAR. She is extremely passionate about science outreach. She believes that the cultivation of scientific thinking is for everyone. Uses astrophysics as a vehicle to engage lay audiences of all ages with these questions in multiple languages, and works for the people's science movement towards this goal. She is also deeply concerned about the inequities in the sciences and attempts to bring an intersectional lens to the endeavors to mitigate them. She is founder and past chair of the Gender in Physics Working Group of the Indian Physics Association and past member of the Working Group for Gender Equity of the Astronomical Society of India. She is vice chair of the Women in Physics Working Group of the International Union of Pure and Applied Physics, past vice chair of the Executive Committee IDSST. In addition to her research publications and popular articles on astrophysics, her published work includes writings on gender inequity as well as science and society. Besides this introduction, let me speak few lines on our new initiative of starting this fourth SOAFAL series, especially on the Lilavati's daughters, women scientists of India. While translating the book Lilavati's Daughters into Odia, I came across this brilliant scientist across different disciplines, and I had a desire that I'll extend rather this already hitherto the SOAFAL lecture which started sometime in 2021 to include these Lilavati's daughters. And I am very happy to mention you that we have already completed 3 lectures. This is the 4th one. And then there will be lectures by Professor Sujata Ramdurai, Professor Tanushree Dasgupta, Professor Bindu S. Bamba, and host of other women scientists. So I have the privilege of introducing our Chancellor of this university, Professor Amit Banerjee, to the audience. He was earlier the Vice Chancellor of this university for almost 5 years from 2015 to 19, then the Pro-Chancellor of this university, and finally he is now the Chancellor. I will request sir to kindly address the audience for briefly for few minutes. After that we will have the lecture by today's speaker, Madam Prajwal Shastriji, on today's topic, meandering into astrophysics. With these words, I once again welcome all of you to this prestigious lecture. Thank you very much. Sir. Sir,
am I audible?
Yourself. Yes,
am I audible?
Yes,
thank
sir,
you
are audible.
I am actually, excited like a child to be able to see in person and to be able to hear Professor Prajwal Shastri today, because she has been a great inspiration for me for a very long time, and it has been so because in particular I found there is something that I share with her. Of course she is at a much higher pedestal and I am a a very mundane person, I feel that India is yet to unleash its scientific potential at the grassroots level and through the ranks. And I remember, a couple of years back, she had written a very beautiful article in the Hindustan Times, The Unscientific Temperament of India. Do you remember that, madam? I kept that newspaper with me, and oftentimes when you discuss these issues, I refer to your article, and it is so well written. It is so it's actually something that comes out from the heart. And also in this university, ma'am, apart from our academic endeavors, apart from trying to build global citizens and in different professional avenues, apart from creating a mini universe by our inclusiveness with our international students as well as our own students, we are extremely proud and extremely fond of maintaining or creating an atmosphere of gender equity. As a matter of fact, ours is one of the universities in the entire nation where we have female faculties nearing 50%. It's actually more than 40%. That is something that we all are very proud of, and we'll definitely throw a big party. You will be one of the invitees when this figure crosses 50%. And we also, have a lot of initiatives for women students, including scholarships and proctorship and other things. So, gender equity has been one of our phenomenal USPs in this university. And you, as a person who looks at gender equity as one of the fundamental tenets of the ecosystem of learning and ecosystem of scientific temperament, makes you so dear to us. So, without feigning to stand between you and the audience any further, and without losing my opportunity of listening to you, thank you very much, ma'am. And if Professor Sharma permits, may I request you to meander on the astrophysic knowledge that you are going to share with us. Thank you very much.
Thank you, sir. Thank you very much. Now it's my privilege to request today's speaker, Prajwal Sastry, madam, to speak to the audience. Madam.
Thank you very, very much. I'm deeply grateful for this opportunity, and also it was particularly heartening to hear your Vice Chancellor mention this article of mine. I'm glad that actually people are reading it. I did write an article, an essay in Leelavati's Daughters, and most of this talk is sort of based on it. So I was born a year after Sputnik was launched. So it was, I think, a very different kind of atmosphere at that time compared to what young people get into today. There were no digital devices, which distracted one's attention from what was happening around us. On the other hand, with Sputnik kind of was iconic and symbolized how science would be the way forward. But perhaps sufficient of warning, shall we say, about what the pitfalls could be. So I will come to that a bit later, but Sputnik was very exciting for everybody, and by the time I remember in my conscious memory, spacecraft and all of that was kind of commonplace. So it wasn't really surprising that Yuri Gagarin and Valentina Tereshkova were my childhood heroes, and I dreamt about being a scientist on a spacecraft. I also was privileged to grow up in a home surrounded, and my parents got me when I was quite young, about 8 years old, this very colorful fantastically illustrated book called The Atom, in which there was a description of Rutherford's gold foil experiment. So, for those of you who don't remember, at that time, atoms were believed to be this sort of cloudy kind of entities, and Rutherford experimented with that idea, and he had a gold foil and he fired very energetic particles at it. And if atoms were these cloudy structures, those particles should have just gone through and been seen, detected on the other side of the foil. But what he found was that some of them bounced back. And this completely changed how people thought about atoms at the time, and they realized that most of the mass of the atom was actually concentrated in the center and so on. And for me, I really, really found this fascinating. And I guess looking back, it was for me a window into what the scientific method was, how the scientific method was about being willing to change your conclusions based on new evidence. Around the same time, maybe a couple of years later, my parents gave me Marie Curie's biography to read. That was tale. Of course, the stark experiences of Marie Curie being a lone woman in her class and so on was very striking, but I always thought of it as something from another time in another place. Another book which made a deep impression on me was this science fiction book called Andromeda, which was a space age tale about space exploration, but it was also a story where from the future, of course, where human beings had constructed a society where they had very open and healthy relationships between them, men, women, everybody. Those days, people who are from my generation may remember that Mead Publisher, which was a publishing house out of the Soviet Union, marketed a lot of its books in India, and many of them were translated. I read many of them in my language of Kannada, not just in English. And there were books on his sort of historical tale, there was fiction, there were children's books for very young age children with beautiful illustrations, and there was a lot of science fiction. So I was brought up on a lot of Russian science fiction at the time. And the other thing from that childhood was that we had this habit of putting a mat on our garden after dinner at night and just staring at the sky. And it was, even though I was in a biggish, I mean, it's not a biggish town, but it was a reasonable town. But we could still see the night sky very beautifully. I could see meteors, the planets, of course, and I could spot occasional artificial satellites. My father taught me how to spot them, how they were different from the other shiny dots that we saw. And at some point in my childhood, a comet appeared, which stretched across the sky very brightly, and it was amazing. I remember doing a painting of it with a mango tree in the foreground. And what was fascinating was much later, when I became a scientist, I realized that this was called Ikea-Sekki, this comet. And there was somebody from Australia who had also painted this comet. I actually lost my painting, and this person actually became my collaborator when I developed an international collaboration with a scientist from Australia. And I was quite fascinated to see that in his childhood he had also painted the same comet, Ikea-Sekki, when it came close to Earth. I could also see the Milky Way. Of course, not like this. This is a picture that a friend of mine has taken from Ladakh, where the skies are extraordinary. And this is a photograph, so with a large exposure. But I could see the Milky Way from my town. Unfortunately, most young people I meet today have never seen the Milky Way with their naked eyes. We couldn't see horizon to horizon like this from my town. That I saw much later when I went to Australia to observe at the observatory there in Siding Spring. I saw something like this with the Milky Way stretching from horizon to horizon. Another very striking actually set of books that I should mention are these books on mathematics by W. Sawyer. And later, much when I was an adult, I learned that Sawyer has been heralded as one of the best mathematics teachers. And his books were really fascinating. I read them when I was in high school, and they gave a very intuitive feeling for mathematics. But more importantly, I grew up with never the feeling that mathematics was something difficult. That is the beauty of the books that Sawyer has written. He makes it a point to give this impression that mathematics is not difficult. And I think that is a very, something very influential in my life. And indeed, that should be the way children should learn mathematics growing up, regardless of whether they want to become scientists or ministers in government or football players or whatever. This is my school. This building, of course, this is a modern picture. This is not something I've taken. It's from the internet. But this picture doesn't give the whole idea of what my school was like, with vast playgrounds mainly. So one of my best memories of my school is how much we played. I remember even going back to school on Saturday afternoons when there was no classes, and being able to make use of the buildings and the surroundings and playing with my friends. That way it was really lovely because there were no restrictions. There was no gatekeeper who said you can't come out of class hours or anything like that. And playing was a huge component of my memories from school. And my college was in the same campus. This is again a picture of the internet. So those days there were no cars parked in the campus. And one of the great things about my college is that I had very passionate teachers who were passionate equally about what we learned in class and what we did in the lab. And outside of the curriculum, also because of some UGC funding that was there, we got to do extra things. Like we had a person come and have us build electronic gadgets by soldering electronic components. There was another engineer professor who came from the local engineering college who taught us Fortran programming, and then we went to Gindhi Engineering College to actually run our programs that we had written and all that. And all that was just tremendous fun. And then I went to the Indian Institute of Technology, Bombay, and this is a photograph of the entrance to the physics department, a very dear place. And there were a lot of professors who were excellent physics teachers, but one of the highlights, I would say, of my masters there were these two professors, Prabhatar Kane and Bhar Vilatkar. This is a photograph of Professor Kane along with his spouse, Dr. Rammu. She was a medical doctor in Bombay. And one of the, I say highlights because they were the ones who made me realize that it wasn't only some big shots like Einstein or Boyle or somebody who made new scientific discoveries. They made me realize that even ordinary people like me could actually create new knowledge by fiddling around in a laboratory. So that was quite amazing for me. And then I went to TIFR to do a PhD. Primarily, I went in thinking I was going to do nuclear physics because that was what Professor Kane did, and I was really inspired to study that further. Also, maybe memories of the Rutherford experiment. But when I joined TIFR, they took us to all their field stations, including this telescope in Ooty that had been constructed in the late 60s. And I met Professor Govind Swarup, who was the sort of driver behind that whole enterprise. And I was completely blown away by the questions that one could ask by doing research in astrophysics. Until then, astronomy was like a hobby for me. I never thought of it as a subject in which I could do research. And I must mention the highlights of my PhD. Professor G. Srinivasan, who is not from TIFR, he was from the Raman Institute, but he treated every student as his own, and he really inspired me to switch. He was the clincher in terms of my switch from nuclear physics to astrophysics. And this is Vijay Kapahi, who I had the privilege of having as my PhD supervisor. And he was a person who treated everything, including questions in astrophysics, with rigor and with playfulness at the same time. And that was something simply amazing for me. And I remember that even now, and I see the influences of that, signs of those influences even now. I then went on postdocs. This is in UT Austin with Beverly and Derek Wills, and these are the other people who also research black holes who were major influences on me: Martin Elvis, Hank Kinney, Meg Urey, and Roger Blankman. So I decided to pick the topic of giant black holes for my PhD, primarily driven by what Vijay Kapahi was doing. And so what are black holes? We can kind of get an intuitive feel for what black holes are by thinking about the idea of escape speed. So all of you probably remember from your high school physics that if we throw something here on Earth, it will fall to the ground. If we throw it faster, it will go further but still fall to the ground. But there will come a speed at which if we throw something, it will actually rotate around the Earth, and a higher speed will take it away from the Earth and escape from the Earth's gravity. And that speed happens to be 11 kilometers a second. So now suppose we imagine that, so for those of you who like formulae, here is the formula for that escape speed. I won't actually go into the details, but if we imagine that the mass of the Earth is squeezed to a smaller volume, then what will happen is that the escape speed will actually increase, because that term r in the denominator will actually reduce. Right? So now, if we take this idea further and squeeze all of the mass of the Earth even further, so much so that the escape speed becomes the speed of light, then nothing can escape from such an object, and that is what we would call a black hole. So that's a very intuitive sense of what a black hole is, and it implies a relationship between the size and the mass of the object if it has to be a black hole. And for the Earth, it turns out that you need to squeeze it to something like a marble size in order for it to become a black hole. And you'll say, oh, that is quite impossible, which it is. But if you think of the sun instead of the Earth, that needs to be squeezed to about a diameter of 6 kilometers. And so then, by the way, are you able to see me or no?
We can't see you, but we can see the screen. We can't see you, but we can see the screen.
Okay. All right, because I was gesturing with my hands, but obviously you can't see that. Okay, so if you squeeze the sun, it turns out that you just need to squeeze it to a diameter of about 6 kilometers in order for the sun to become a black hole. And if you remember Gargantua from the film Interstellar, Gargantua is even less of a squeeze because it was given a mass of 100 million suns. So then when it is squeezed, it is much less of a squeeze. And the reason why Gargantua was made to look the way it is, which is correct, is the correct physics picture, is because if some material comes near this black hole. It will be drawn by the gravity of the black hole, and it will swirl around the black hole, because typically no material will, or most of the material will not be directed exactly towards a black hole. And so when that material is drawn towards the black hole, it will first swirl around the black hole and then plunge into the black hole. In the process of swirling, it will be accelerated to extremely high speeds and therefore heated, and therefore that material will glow. And this is the reason why Gargantua looks the way it does, because the swirling matter glows, and that enables us to spot such black holes in the cosmos. And these are giant black holes. Gargantua had a mass of 100 million solar masses. And so then they become beacons in the cosmos, which we can spot to very, very large distances. So you will perhaps remember that Andrea Ghez won the Nobel Prize along with Reinhard Genzel and Roger Penrose for the discovery of such a black hole in the center of our Milky Way. So that's the nearest giant black hole we have, a very real black hole. And the result from Andrea Gez's observations is something I really love, and so I want to share that with you. So what you see here is infrared images of the very, very center of our Milky Way, which the position of that is shown in the top left image, where you see the Milky Way and the center is marked by a circle near the Sagittarius teapot spout. And that area was imaged by Andrea Ghez and also by Reinhard Genzel using an infrared telescope. And they took images continuously starting in 1995. And then put all these, what I'm showing you here is all those images put together to make an animation which shows us how the stars move. So what you're seeing in this image, the multicolored splotches are real stars, so those are real data. And the curves that you see are, of course, meant to guide your eye. So the multicolored splotches are moving, and just see how they move. You can see the date at which the image was taken in the top right corner. And so you can see that these multicolored splotches are not moving in straight lines. They are not moving randomly. They are all moving in elliptical orbits. And not only that, the focus of the elliptical orbit is the same. And that is marked with that crosshair that you see over there. So what this means is that all these stars are being driven by the gravity of a very dark but very massive object. And using the same idea that I mentioned earlier, one can calculate what is the mass. It's a dark mass because we can't see light from it. What is the mass of this object which is driving all these stars in elliptical orbits? And it turns out that the mass is 4 million times the mass of our sun. And the other thing to notice is the fact that the closest approaching star, the one with the yellow curve, you see that it approaches very close to that crosshair, but then continues along its path, which means that this dark, heavy object of 4 million solar masses is to be smaller than the closest approach of this star. And so if you put all this together, it becomes clear that the darker object at the center, in that position of that cross, has to be a giant black hole. So that's the result that got the Nobel Prize, and these are the kind of objects that I chose to study for my PhD. Of course, that was much before Andrea Ghez did her experiments. My PhD was much earlier, but at that time we didn't know about the exact masses of these black holes, but we knew that there had to be something like that to explain some of the things that we saw. So in order to study these objects, one has to use telescopes at multiple frequencies. So I've given some examples of those. These are telescopes that are based on the Earth and operating in visible light, in radio light, and so on. The one at the bottom is a telescope which didn't exist when I was doing my PhD, but some of my students have used it, and it's a very, very powerful telescope that gives us extremely interesting results, has been giving us extremely interesting results over the past several decades. And we also need to put telescopes out in space because we have the atmosphere surrounding the Earth, which is not transparent to some of the light that we see, for example, X-rays or gamma. So these are the kind of facilities that I have used, and I also will show you some images. But when I say that these are images that are taken in radio light or infrared light or X-ray light, what do I mean by that? Because the eyes cannot see any of this. So astrophysicists use what we call false color images to render images that are taken in radio light or gamma ray light. And this is an example of such a false color image. It's a false color image of a cat taken at infrared frequencies, and you can see that the nose is shown to be white and the ears and eyes are yellowish. That's because infrared light is emitted as per how warm or not the body is, and the cat's nose is cold and the ears are warm, so the amount of infrared light that comes from these two is different, and that difference is shown by these colors. So the colors are not real colors, that's why we call them false colors, and each color represents just the intensity of the light that we see. This is another such example to show you that the choice of colors is completely arbitrary, and such images have meaning only when you have a key that explains what color is what intensity. So coming to the cosmos, here's a true color image, so-called, of a galaxy that is showing you a bunch of stars and also a dark lane in the middle and so on. And these are images of that same galaxy taken at X-rays, in visible light and in infrared light. And I hope you can see the bluish colored X-ray light image, the greenish colored visible light image in false color. These are all false color. And the infrared image, which is sort of red and yellow. And you can see that they tell us very, very different things about the galaxy. And this is why we need to observe things in the cosmos at different frequencies. And I illustrate that with this image at the bottom left. You can see Saturn, as you're familiar with, in visible light, and then lower than that is the image taken in radio light, and it looks more or less the same. But if you look at Jupiter, the visible light image looks very different from the radio image, which is shown at the bottom. And the radio image tells us actually that Jupiter is
Nachiketa, can you hear her voice? I have lost her.
No. We are also not able to hear her voice.
Prof, can you go back a little bit, because I think past about 20 seconds we lost your voice. Hello?
Hello. Madam. Should I call her?
Try.
somehow I got muted. Can you hear now?
Yes.
Yes, now we can hear you.
Now.
Okay.
Can you go back to the explanation of Jupiter, because that is where we lost you.
Okay.
Up till Saturn we got you, but at Jupiter we lost you. We lost the voice.
Okay.
Yeah.
Okay, so I was just explaining why it is important to observe objects in the cosmos at different frequencies. So this is Saturn, as you would be familiar with, in visible light. And this is how Saturn looks in radio light, which is more or less similar. But if you look at Jupiter, in visible light, it looks like this. But in radio light, it looks very, very different. And what that tells us is that Jupiter is also a very large magnet. So we will miss information if we don't look at cosmic objects at multiple frequencies. So this is a piece of sky which is showing you multiple objects, stars here and there and so on, but also a galaxy of stars in the middle. And this is the visible light picture. Now, the same galaxy observed in radio light looks like this. So here, the radio light false color picture in pink is being overlaid on top of the earlier image that I showed you. And you can see that you can some sort of streams of stuff coming out from the center of this galaxy and going out into intergalactic space, creating a very, very large structure. So imagine that galaxy is very, very large. It's much bigger than even our Milky Way. And so this structure with stuff streaming out is the easiest way to see them. So we have many such examples, and I've shown a few examples here. And one of them is called Messier 87, and this is a false color picture at radio frequencies. And this you may have read about in the newspapers, because the central black hole, it was known that it must have a central black hole because that's the only way we can create these kind of mega structures of streaming plasma. But actually, the silhouette of that black hole was measured by a very sophisticated telescope. So, on the top left, you see the galaxy itself with all the stars. In the middle, you see all this stuff that is streaming out. If you zoom in, what I'm showing you on the right side of the image of the slide is the stream, the structure of the stream when we zoom in. So the blue image is a false color picture at radio frequencies. The same thing is seen in visible light as well when zooming in. And finally, in X-ray light, I'm sorry, maybe you can't see this because it is hidden by the screen, but it looks very, very, very similar to the other two. And we also know that these streams must be coming outward from the center, because radio images even further zoomed in have been taken at different times and put it together to form an animation for this particular galaxy. And you can see at the bottom left this animation, which is just images put together, taken at different times, and you can clearly see movement from the center outwards. Now, how does this actually happen? Do we understand? Yes, we understand somewhat. So Roger Blanford and Zayek came up with a hypothesis to explain this in 1977. So they said that if you have a black hole that is spinning, and if you have very strong magnetic fields near the black hole, then this kind of streams of plasma can be generated, which are very, very powerful and which can go out into intergalactic space. And next slide is a computer simulation of their idea. And the computer simulation does in fact show us that this kind of a thing is possible. So this is an idea that has gained a lot of support in the literature. And now I will show you that simulation. So here the green lines represent magnetic fields, and the colors, the cloudy colors, represent stuff, material. And you can see that these magnetic fields are twisting and turning because of the spinning black hole and are generating these streams of plasma. So basically, most of the stuff that comes near the black hole plunges into it. Stuff is thrown out in these streams because of the magnetic field. And here is the zooming in to the even further to the very center of this galaxy by a sophisticated telescope called the Event Horizon Telescope, which is actually a collection of telescopes all across the planet, and these were able to zoom in 1,000,000 times, which means it's like me sitting in Bengaluru and reading a newspaper in Delhi. That is the kind of zooming in. And what did they come up with? The silhouette of the central massive black hole. Black hole is 6 billion times the mass of the sun. The same thing was done for the center of the Milky Way. So I had explained that Andrea Ghez and Rainer Genzel and their teams had determined that there was a 4 million solar mass black hole in the center of our Milky Way. The same result was confirmed with this independent technique of imaging the silhouette of that black hole, and the two results are very consistent. So this, is the power of science. You had a telescope in Hawaii, Andrea Ghez, a telescope in Chile, Reinhard Genzel, and both of them came up a mass for the black hole in the central Milky Way of 4 million solar masses, and then the Event Horizon Telescope imaged the silhouette, and they were able to calculate the mass as the same result. And at the bottom is shown a computer simulation from NASA, which tries to model what would happen if you had a 4 million solar mass black hole, and and if you had material coming very close to it, how it would look. And that again confirms the previous two results. So it all falls into place, and that is the power of science. Of course, if it didn't fall into place, it's not something that people would dislike or get upset about. It would simply mean that we don't have a complete understanding of what we are looking at, and so it would just stimulate more research and more, which would then lead to more understanding. This is an example from my own work. So there is this galaxy which is called the Karaf galaxy, which is at the bottom right of the image. The visible light telescope at Siding Spring Observatory in Australia, a radio telescope called the Australian Telescope Compact Array, and the Chandra X-ray Observatory, which is, I think, hiding behind the screen, but that's okay, you will see it in the next slide. And putting together the results from all of these, so here you can see the three telescopes that we use. Putting together the results from all of these, what we found is that the two central black holes of the two galaxies that came together to merge and coalesce into this third galaxy shine in radio frequencies and also shine in X-ray frequencies. So it confirms that both of them have this swirling stuff going around them and possibly generating streams, but still baby streams of plasma, which to us are simply visible as these splotches in the radio image. And so basically we confirm that there are two Gargantua-style black holes because there were two galaxies to start with, which came together to make this galaxy that you see now. So this is a picture of what I think I'm most happy about over the career with black holes that has lasted about 4 decades. So here's Govind Swarup right in the middle, who was my first inspiration to come into astrophysics. And then there should have been Vijay Kapahi, but we lost him rather prematurely, so I have a photograph of him there. And the others are all my PhD students who are now astrophysicists in their own right, experts in the physics of giant black holes. And and here are a bunch of my intern students who have gone on to do astrophysics PhDs. Most of them have finished or they have done something related to astrophysics in terms of making instrumentation for astrophysics. And so it is my hope that this excitement will continue to excite more people. I mean, like the way I give this talk here. Of course, these kind of talks are just one-off, and I don't get to meet the people who listen to those talks, and so I don't know what they are going to be doing or they have done in their future. But I hope that all of them are able to share the excitement. I don't necessarily wish that all of them become astrophysicists. We also want people to become dancers and make movies and play football and become ministers and managers and so on. But what I do hope is that all of them will be able to share the excitement of the new facilities that are coming up. So on the top left is the James Webb Infrared Telescope, which is 1.5 million kilometers away and has already got amazing results over the last couple of years that it has been observing. And in the center is a new telescope called the Square Kilometer Array, which is going to be half in South Africa and half in Australia. India is also a partner, and this is a radio telescope, and it's the biggest telescope ever constructed, and we look forward to extremely exciting results from it as well. So I want to go back to Andrea Ghez. Andrea Ghez, as I said, won the Nobel Prize in 2020 for physics. She once said that I grew up hearing the word no all the time. You're a girl, you can't do it. You're a girl, there's no way you can get into MIT, etc. So the thing is that I would have been very surprised if I had heard this while I was growing up, because in my school or in my college, never did I ever hear any teacher tell anybody, me or even the others, that a girl cannot do science or a girl cannot do research. But unfortunately, going into the more elite institutions like the Indian Institute of Technology, Bombay, where I did my master's, or even worse, the TIFR where I did my PhD, there was a lot of this being said. And I want to point out to you, it's a very difficult thing, but it is really, really important for all of you to realize that there is absolutely no evidence for this. So, we are all scientifically thinking people. We may not all be scientists, but we must be scientifically thinking people, because that is the way forward in this world. And there is this idea that there is a lack of interest in science among girls, which is completely wrong. There is no evidence for it. We have published these results which show that women's enrollment in undergraduate science is 43%. The prestigious Inspire fellowships for all of sciences are won by more girls than boys, and for physics are half and half. The Indian Academy of Sciences summer fellowships are won by many more women than men. And so it is important for both women and men to realize that this is not based on the evidence. What is worrying is this result, which is a survey published in 2018 of high school students, where the survey is asked about perceptions of these high school students and asked them, is it correct that fewer girls than boys are interested in higher studies in science and math? And more boys than girls said yes, more girls than boys said no, and more boys than girls said don't know. And they also asked, is it correct that science and maths are difficult and girls go for easier subjects? And again, boys and girls said yes. So it seems that boys and also some girls are socialized to think that girls are bad at science. And this is something that all of us need to be mindful of. It is completely without evidence. Therefore, it's a very unscientific idea. And if there are fewer girls or fewer women in science, that is because there are obstacles to them. It is not because they are not good enough or they don't want to do science or they are incapable of science. It is because they are being stopped from doing science despite everything. And I say that everybody needs to be mindful of it, because this is not just about doing science. It is about scientific thinking itself. Because if this kind of idea gets perpetrated, then it will be that only men can have scientific thinking, which is again an absurd idea. And it is really, really important for all of us, for the whole society, for the whole world, to go forward with scientific thinking. Meaning, as much belief as there is evidence. Meaning, what Rutherford did. That is the willingness to change our conclusions based on the evidence. So, scientific thinking is something which is for everybody. You need scientific thinking whether you're a dancer, whether you're a footballer, or a government servant, or a manager of an enterprise, whatever it is. And that is something absolutely essential, and that is something that we all need to strive. In fact, our constitution says that it is the duty of every citizen to strive to develop scientific temper among all of us. And so this is why I volunteer for the People's Science Movement. This is why many of us marched for science starting in 2017. These are some pictures from the March for Science in Bengaluru. And also, it is important to ask questions. Scientific thinking essentially means asking why. And it is asking why without any hesitation, without fear, which is the essence of scientific thinking. And you will remember at the beginning of this talk, I talked about how I used to be excited about spotting satellites in the sky. That was more than 50 years ago. This is what we have come to now. All of this is space debris. So I would not have been obviously happy to know this. This didn't exist more than half a century ago, but it shows us that we haven't asked why enough. We, meaning we as citizens of the world, haven't asked why enough, and that is why we have such a mess, both on Earth and in space. And so, from the People Science Movement, one of the things we've done is produce this book called Ask Why. It was designed and composed by an organization called Navnibiti, based in Bombay and Pune. And the book is a WhatsAppable book of 30-odd experiments. We've translated it into different languages, and it has some very, very simple experiments from equipment that can be self-constructed. And I encourage all of you, regardless of whether you want to do science or not, to get hold of this and do these experiments. I also took it to Ethiopia once when I went there to attend a conference, and I visited a school there as part of their outreach activities, and talked about these experiments with the school children there. So ask why. That is really what we all need to do. I think I will stop here and take questions.
Thank you, madam. Thank you very much. I think you should stop this sharing so that we can see you, and then we.
Can you hear me?
Yes, ma'am. Yes, thank you very much for a scintillating talk. And now I think we'll have few questions, and I will request you.
Nachiketa, you have now been muted.
Am I audible now?
Yes, you are audible now. Yes.
Okay. So let me ask you a question, madam. What kind of matter exists in black holes? And if nothing escapes from black holes, how to locate them?
So we don't know what is inside the black hole. So whatever approaches the black hole enters it, and then we have no information. That is the special thing about black holes, that we have no information about whatever is inside the black holes. And how do we locate them? One of the ways is how I described. That is, if you have matter which approaches a black hole, then is drawn to the black hole and it swirls around it. In the process, it's accelerated and then heated, and it glows. And that glow is extremely, extremely powerful. It's more powerful than all the light from all the stars of the galaxy put together. And so then it's very easy to spot these things in the cosmos. So this is one way in which we spot black holes. There are a couple of other ways, but this is an important way in which we are able to spot, especially giant black holes.
Thank you, madam. Any other questions?
Good evening, ma'am. Myself Sonali Dash. And ma'am, here is my question is, how does Jupiter's magnetic field compares to Earth's and what effect does it have?
So I don't, I'm actually not an expert on Jupiter, so I don't remember offhand what the strength of the magnetic field is. You could easily look it up. The effect it has is to create these plasma streams and all that, which is what gives rise to the radio emission which was seen in that image. So that is the consequence, one of the consequences. Possibly it could have consequences if there is some radio transmission that is attempted from within the sphere and all that. But so far, I'm not aware of anything like that. But here on Earth, we can just we are able to see the effects of it. It's not going to impact any radio transmissions, etc. here on Earth.
Good evening, madam. Myself Deepak Kumar Patnaik. I am asking that we know that near the black hole the space is.
I think the person got muted.
Hello, madam. My question is, we cannot see the space. We cannot touch the space. Then how it is carved? What is the concept which behind the curved space? Means we cannot see the space. We cannot touch it.
Yeah, we can't see the space, but we can see light as it travels across space. And we have seen the effects of the curvature of space-time using light. This was something that was done very early by Eddington, a few years after Einstein proposed his theory. And so we can see the curvature using light. We can also see gravitational redshift because of the curvature of space-time, which changes the frequency of the light. So we see that every day because GPS satellites are far away from Earth, and so the frequency at which the transmitter emits on the satellite is slightly shifted by the time it reaches Earth. And similarly, the frequency of transmissions from the Earth is slightly shifted by the time it reaches the GPS satellite, and this is because of the same effect.
Myself, Professor Ramarao, madam. Thank you very much for the nice talk. Can we estimate the mass of a black hole, madam?
Yes, so it depends on a few things. As you saw, the mass of the giant black hole in the center of the Milky Way was estimated because the motions of the stars around the black hole was measured, and by applying the Keplerian formula, they estimated the mass of the black hole. When the silhouette of the black hole is imaged, which has been done for two black holes, the one in the center of the Milky Way and the one in the center of this galaxy called MESI-87, which I showed you, from that silhouette using general theory of relativity, the mass can be calculated. But giant black holes are not the only black holes we know. There are black holes of much smaller mass. So the smallest black holes we know are those which are a few times more massive than our sun, and we know that they are a result of stellar collapse. So when a star which burns due to nuclear burning when it exhausts all its fuel, then there is nothing to hold it up against its own gravity, and so it collapses. And if it's a very massive star, it won't happen to our sun, but if it's a very massive star, then it could collapse into a black hole. And if such a black hole gets gravitationally bound to another star, then it forms what is called a binary system, two stars, so one black hole and one regular star. And in that case, we are able to measure the effect of the black hole's mass on the other star, because both of these will be, because they're gravitationally bound, as seen from Earth, they will be rotating, and therefore we will see the effect of that rotation on the properties of the other star, and from that we can estimate the mass of the black hole. So again, using Keplerian physics and so on. So such stellar mass black holes, we know about 75 candidates in our own Milky Way, and a few of them have very well determined masses. Another way of determining the mass of a black hole is if we can see, we can measure the coalescence of two black holes using gravitational waves. So since 2015, we have a gravitational wave observatory which is able to detect gravitational waves from coalescing black holes, and they have measured masses for many black holes now, including a black hole with a mass of about 175 solar masses. So these are different ways in which masses of black holes can be measured.
Thank you, madam. Thank you, madam. Any other question? Yes, please.
Good evening, ma'am. Myself, Chitralipi Nayak, and my question to you is, what happened to the space-time when the cosmic objects they collide in the space?
So space-time is distorted when two objects collide. I mean, it's distorted. Even if I were to collide with you, it would distort. It's just that it's very small, and so it's immeasurable if that happened. So to be able to measure that distortion, it requires two very massive objects to collide, and that's exactly what the gravitational wave observatory measures. It measures the ripples in the space-time when two black holes coalesce, or when two neutron stars coalesce, or a black hole and a neutron star coalesce, etc.
Any other question?
Very good.
You're muted.
Very good evening, ma'am. I am Amrita Sahu, and my question to you is, as you have stated that women in science has been a prejudice for a long time in our society.
Sorry, would you repeat that?
As you have stated that women are not good at science, it has been a prejudice and it's still prevailing in some areas of our society. I still believe that as you have been into astrophysics at that time has made a change for us, and it's a motivation for us, we can say. But still, what are the opportunities today's female can grab on to pursue on the subject or the course of astrophysics?
Okay, so I hope I made myself clear. I said that the idea that women can't do science is a myth, right? It's a wrong idea. There's no evidence for it, and it's therefore simply a result of patriarchal ideas in society. So it's a wrong idea. I hope I made that clear. I showed evidence that it's a wrong idea. So it's not just about me having done astrophysics, which is what demonstrates it. It's every evidence you can look at argues against that idea. So that idea is wrong. So everybody needs to wipe out that idea from their heads, whether you're men, women, senior, junior, babies, adults, whatever. So that idea needs to be discarded. In terms of opportunities, it's the same opportunities that are available to everybody. It's the same opportunity. There are no different opportunities for women. Of course, there are very specific schemes or scholarships or so on, in some cases which are aimed at some marginalized groups, because of the need to correct for historical injustices or contemporary injustices, and that includes certain schemes and so on for women as well, or for Dalits, or for colored people, etc., etc. And those are necessary because otherwise, the progress towards an equitable scientific enterprise will be extremely slow unless we correct on a very urgent basis for both historical and contemporary injustices. But you should think of it as, and so if you come across such programs, you should make use of them, but you should see all opportunities as open to you.
May I add? Nachiketa, I
Yes,
would
please.
like to, she asked about the opportunity, so I would like to repeat what I had said even in the last this thing, that the three science academies of India, INSA, NASI, and our academy, the Indian Academy of Sciences, there's a SRF, that is Summer Research Fellowship Program, that happens every year. Okay, and college students like this young lady who has asked this question, they are all invited to send in their applications, apply for that, it is available online. Apply for that, it's a 2-month program that happens during the summer vacations. So during those programs, as Professor Shastri showed us, that we engage these students, we send them to work with these kind of professors in their research organizations. So they, all their staying, rehan sehen, their travel, all these expenses are taken care of. A stipend is given to them for the for this course, during the course of these 2 months. This kind of information and this kind of facilities programs are available already. So if the students are interested, they should just go to the website of the academy and take these opportunities and apply for them, so that they get an opportunity to really work with these people, internship programs. So this is one of the programs that is running, and there are several others like this. Yeah, and as Professor mentioned, it is not really that women are bad in science. The perception, unfortunately, among human beings and in our society currently, unfortunately, the perception is hugely distorted. That is one thing we need tremendous corrective measures for. Yeah. So I encourage you to look up this Indian Academy of Sciences website and check out this SRF program. This is a very good opportunity, and we make internships available.
Thank you, Subhankar ji. Yes, ma'am, please.
I wanted to add to what Subhankar just said. So, if you remember, I had shown a slide where we had done a study of exactly the Academy's summer fellowship program, and we had found that this program actually has more than 50% women who are successful at getting the scholarship. And so this is a program where we feel that the process is carried out well. So it is not biased against women. I want to point out that yes, it is a societal patriarchal problem, but it is very prevalent within scientific institutions. So it is not just that outside society is biased against women. Inside scientific institutions, scientists are biased against women. Both men and have prejudice that is there in outside society, and this prejudice increases. The data show us that this prejudice increases as you go to more and more elite institutions. So if you remember what I narrated to you about my own personal experience, I did not experience any kind of negative comments or bias or anything. Neither did any of my classmates. I went to a girls' school, a girls' college. There, none of my teachers, who were from both genders, we had men and women teachers, both in school and college, and none of them made any negative remarks about women doing science or the competence of women. But such remarks were constantly made when I went into IIT. It was even worse when I went into TIR. So it is well, we have also written a lot about this, about gender bias within scientific institutions, which is creating barriers for women to thrive as scientists. So for the young people in the audience, what I would say is you should be really discerning when you choose the kind of scientific institution you want to work with. So the internship is a very good opportunity for you to try out these scientific environments because you get to know firsthand how respect for work culture they build a work culture that is welcoming of everybody and all of that. So it's a very short period, it's just 2 months or 3 months. So it's a very good opportunity to sample an institution that you might think is a future place where you want to work. And also, when you pick institutions, you should. I mean, obviously, on the website, you can't make out whether it's a nice working climate or not. So you need to dig deeper. You need to talk to people who have been there before, younger people, your seniors who've been there before. Talk to them and see what it was like for them. Was it a nurturing environment? Competitive environment. Being an overly competitive environment, in my experience, is not a nurturing environment, and so on and so forth. So you need to dig deeper and determine what is a good working climate, and sort of have that as also a priority, not just the sort of academic discipline that you want to work with or something like that.
Thank you, madam. There is a question in the chat box. Does time stop when you fall into a black hole? How does a black hole affect time dilation?
So, as seen from outside, a person who is trying to enter a black hole it may seem like sort of time is slowing down for them and it's kind of going. So it depends on the reference frame that you use. But in the reference frame of the person, as you will remember, those of you who've seen Interstellar, the protagonist was able to enter the black hole. So it depends on the reference frame.
I think if there are no questions, we will stop here. So, Subhankar ji, have you got any question?
So I just wanted to say thanks for arranging this. Prajwal ji is one of my favorite, communicators because you have seen how beautifully simple she makes those
Yes,
high
yes,
fund
yes,
so that
yes.
young people can understand. And so she is one of my favorite science outreach kind of people. So this is I tremendous thanks to Prof here and to you Nachiketa for doing this wonderful, bring this wonderful the young people and these beautiful people together because this is how we make sure that more and more curious people take up science as in their career path. It's not necessary that everybody has to be a scientist, no, but everybody has to think like a scientist. That is important. Yeah. So thanks so much on behalf of Women in Science from the Academy Trust and from all young people and from me personally. Thank you, Nachiketa, and thanks, Prof, for being here with us.
Thank you,
Thanks very
madam.
much for having me.
Thank you, madam. Thank you very much on behalf of the university. We are extremely grateful to you. And let me announce the audience that the next speaker will be Professor Sujata Ramdorai, and the talk is on 6th July. 6th July, I think the first Saturday probably. So with these words, I am extremely thankful to today's speaker, madam, and we will also be looking for the books that she has mentioned. I will personally write to her to know about the books so that we can purchase the books and try to translate those books into Odia so that that will be available to many students reading in vernacular medium schools. With these words, again, I am thankful to and due to V.S. Sastriji, I could connect fast to Prajwal madam. So on behalf of the university, we are also in absentia thankful to Sastriji. With these words, I am again very happy and grateful to you, madam. Thank you very much. Thank you.
There's one thing. Can I add one thing? couple of
Yes, please, please.
The mathematics books that I mentioned by William Warwick Sawyer,
Yes.
there's a whole archive of William Warwick Sawyer, which his daughter had, which is now with the Navnirmiti organization in Pune. So I wanted to mention this. So his notes and whatever. He's written a lot of published books, but also his notes and things like that. So that is one thing I wanted to mention. The other thing I wanted to mention was that this book of experiments, a very small book. It's WhatsAppable, so I can send it to you. Like after we finish this call, and so Odia is not a language in which we have it yet. So if you can arrange for its translation in Odia, that would be fantastic.
Oh, we'll do it, madam.
Nachiket,
We'll do it.
he's a clear translator himself.
Because we have a very good translation unit, so we will translate it. We will definitely translate it. Thank you, madam. Thank you very much.
Thank you.
Thank you. Subhang, eh? Oh, अच्छा.